In this video, we're going to talk about the idea of continuity. So a function f is continuous at a number a if the limit as x goes to a of f of x equals f of a. So this is how we define being continuous at a point. Now there are three parts to this definition. First, we need f of a to exist, meaning a is in the domain of f. Second, we need the limit as x approaches a of f of x to exist. And third, we need the limit as x approaches a of f of x to be equal to f of a. Now this third one looks like what we define continuous to be, but for this to make sense, all three of these properties have to be satisfied. And now closely related to this is if a function is defined near a point a and f is not continuous at a, we say f is discontinuous at a. Now, like I said, this is very close in definition to being continuous. As to the definition of continuous, it's just not continuous. But it tends to be the case that we actually look for places where we're not continuous or discontinuous, rather than places where we are continuous when we're looking at main graphs. And so let's look at the following example. And so we have the following graph of the function f of x. And now in this graph, there are three places where this function f is not continuous, or where it's discontinuous. So we have that f of x is discontinuous at x equals 1. So notice at x equals 1, the limit does exist. So the limit as x approaches 1 of f of x does exist. But 1 is not in the domain of this function. There's a hole there. And so that's a place where we would have a discontinuity. Next, we have at 3, it's discontinuous. In this case, the limit does not exist. So the limit as x approaches 3 of f of x does not exist. And at 5, we are discontinuous. And in this case, the important thing to note is that at 5, the limit does exist. The limit as x approaches 5 of f of x exists, but does not equal f of 5. We have this point up here is where we're f of 5, and that's not where the limit approaches. The limit approaches this point down here. And so we can see each of those three conditions that we mentioned for continuous have a potential to fail. In the first one here, the limit exists, but f of a is not defined. The second one, at 3, we have the problem that the limit did not exist. In the third one, both the limit existed and f of a existed, but they just weren't equal. And so we can have points where we're discontinuous for each of these three possible situations. So now let's look at a formula and check for continuity in that case. And so if we look at the following example, we're going to look at f of x equals the function x squared plus 5x minus 7 divided by x plus 3. And so notice in this function that f of negative 3 does not exist. We simply can't plug negative 3 into this function because we would be dividing by 0. And so this function, f of x, is discontinuous at x equals negative 3. Now it turns out, we'll talk a little bit later, that this function actually will be continuous for all other points other than negative 3. And we'll justify that in the future. So now another example, so we could have g of x equal to x squared minus x minus 2 over x minus 2. And we could have it equal to 1. So it's going to be, when x is not 2, it's going to be x squared minus x minus 2 over x minus 2. When x equals 1, or x equals 2, I mean, the function will be equal to 1. And so here we have that g of 2 is equal to 1. So now we need to check, is the limit as we approach 2 equal to 1? So we want to compute the limit as x approaches 2 of g of x. Well, for every point other than 2, we're going to use the top formula in this piecewise function. So we're not actually plugging into, we're just getting as close to 2 as possible. So this will be the limit as x goes towards 2 of x squared minus x minus 2 divided by x minus 2, which equals the limit as x approaches 2. We can factor the top as x minus 2 times x plus 1. And we're dividing by x minus 2. And so notice that these cancel off, so the x minus 2's can cancel in the limit. We'll flip the limit as x goes to 2 of x plus 1, which then gives us 3. And so we have that the limit as x approaches 2 of g of x equals 3, and that's not equal to g of 2, which is 1. And so this function, g of x as we've defined it, is not continuous at the point 2. However, if we changed it slightly and just said h of x is going to be x squared minus x minus 2 over x minus 2, if x is not 2, and 3, if x is equal to 2, then this function, h of x, is continuous at x equals 2. Because in that case, the limit would be the same. All I did is just change the 1 to a 3 from g of x. And so we know the limit of h of x, would, as we approach 2, would be 3. And that's what the function is actually defined to be. And so we could fix g of x, in a sense. This function could be fixed to make it continuous at that point. And so these two discontinuities between the discontinuity we had for f of x that we looked at here, this function, we're just not continuous at negative 3. There's not really a way to fix it because we can't divide by 0. If you actually compute the limits here, you'd see that we go off to infinity and negative infinity as we approach negative 3. But with g of x, we could fix the problem. We weren't continuous at 2, but if we just changed what we were defined to be at 2, we could make the function continuous. And so this brings up the situation that there are 3 types of discontinuities that can show up. So we're going to look at types of discontinuities. Now, the best way to view these is with a graph. And so the first looks something like the following situation, where we just have a hole in the graph. This is called a removable discontinuity. And now we say it is removable because we can get rid of the discontinuity by just filling in the hole in a sense. If we just define the function to be equal to that value, whatever the limit is, at that point, we get rid of the discontinuity and we'd then be continuous. Now, one thing to note is that if the graph is defined just as a different value there, this is still called a removable discontinuity. We can still remove the discontinuity by just defining the function differently. And so in our situation above with the function g of x, we had a removable discontinuity at 2 because we could fix it. By just changing the 1 to a 3, we could remove the discontinuity. And so it is what is called a removable discontinuity. Now the second kind of discontinuity is something like the following. And so here we have a vertical asymptote at this point, which we're going to call A. This is called an infinite discontinuity. Okay, so in an infinite discontinuity, we have a vertical asymptote. And so that was what was happening in our function f of x that we looked at before. Just a reminder, the f of x we had was x squared plus 5x minus 7 over x plus 3. And so there was a removable discontinuity at -3, which is obviously not the graph I drew. Because not a removable, there's an infinite discontinuity there. Because as we go off towards A, or to -3, we are going off to infinity. Now it is also called a removable discontinuity if you have a vertical asymptote and you go off to infinity in one direction and negative infinity in the other. This is still called an infinite discontinuity. Okay, so if there's a vertical asymptote, it's an infinite discontinuity. And there's not really a way to fix these infinite discontinuities, as we're just kind of going off to infinity. Now there's a third type of discontinuity that we can have. And so this third type of discontinuity looks something like the following. And so this is called a jump discontinuity. And so in jump discontinuities, we have jumped values, basically. We were doing something along the bottom, and then all of a sudden we jumped to another value. And now with jump discontinuities, we can sort of fix them, but we have to move the entire graph up. And so we'd have to move this entire piece up so that this point lines up with that point, and it requires a lot of kind of fixing. And so while it could be fixed, the function has to be dramatically changed in order to fix a jump discontinuity. And now, a jump discontinuity can also happen if you aren't defined at this point. So if we weren't defined there, if it was just an open circle there as well, that'd also be a jump discontinuity at that point. So you don't have to be defined at that point. You just have to have a jump in values all of a sudden. And so this will be a place where the limit as x approaches a from the left does not equal the limit as x approaches a from the right. But both are finite. And so those are the three kinds of discontinuities that we can have in a graph, or in a function, which we can graph. And so now, kind of like with limits, how we have this idea of one-sided limits that we just used, we can also have one-sided continuity. And so a function, f is continuous from the right at a number a if the limit as x approaches a from the right of f of x equals f of a. And similarly, a function f is continuous from the left at a number a if the limit as x approaches a from the left of f of x equals f of a. And so we can have this idea of one-sided continuity, just being continuous from one side if we're just approaching from the right or from the left. And so here we only have to check the one-sided limits, which makes this a lot easier of a situation to be in. If we look at our jump discontinuity, if we were to find here, this point was defined again, then this function would be continuous from the right as we approach this value a, and not continuous from the left. And so it's possible to be right continuous and not fully continuous. And similarly, you can be left continuous and not fully continuous at a point. And so now this brings up the following definition. So we say a function f is continuous on an interval a to b if it is continuous at each point in the interval a to b, it is right continuous at b and left continuous at, oh, I got that wrong. It is right continuous at A and left continuous at B. So to keep track of which one's which, it's the one that makes sense to you, for you to do. And so we are continuous on the whole interval A to B, and then we're approaching B from the left, so we have to be left continuous at B, and we're approaching values of A from the right, so we need to be right continuous at A. And so basically the left and right continuous on the endpoints is just because we're not defined to the right of B, so we can only be left continuous there. And similarly, we're not defined to the left of A, so we can only be right continuous there. And so we want to now check the following. So we have the following example. We want to show the function f of x equals the square root of 9 minus x squared is continuous on the interval -3 to 3. And so to do this, first we're going to check the middle values, everything between -3 and 3. So if -3 is less than a and less than 3, then we have that the limit as x approaches a of f of x equals the limit as x approaches a of the square root of 9 minus x squared, which by limit properties is the square root of the limit as x approaches a of 9 minus x squared, which is equal to the limit, the square root of the value 9 minus a squared, because we can plug a in since 9 minus a squared is going to be non-zero. And so this then, notice, is equal to f of a. And so the function f of x equals the square root of 9 minus x squared is continuous for all a in the interval -3 to 3, keeping an open interval. Now similarly, we can check the argument goes the exact same way, that the limit as we approach -3 from the right of f of x is equal to 0, and that's f of -3. And the limit as x approaches -3 from the left, or 3 from the left, of f of x is equal to 0, which is equal to f of 3. And so we are continuous the left at 3 and from the right at negative 3. So we satisfy the conditions to have continuity on the full interval. And so f of x equals the square root of 9 minus x squared is continuous on the interval negative 3 to 3. Because it's continuous for everything in the middle, and we have the needed one-sided continuity at the endpoints. And so now this idea of being continuous is really easy to see in a graph. In a graph, basically all this means is the following. So in a graph, a function is continuous on an interval a to b if you can draw the graph from a to b without lifting your pencil. Now, this is obviously not a very technical idea, but this is a good way to check from a graph if you're continuous on an interval or not. As we talked about before, the three ways we can have a discontinuity are we can have a removable discontinuity. If it's removable, you had to jump over the point that was removed that you could fill in. If it was an infinite discontinuity, you were going off to this side, and so you then had to stop at some point to draw your arrow, so you had to lift your pencil. And with a jump discontinuity, you had to jump values. Since you had to jump values again, you had to lift your pencil. So that's a nice way to check from a graph if you are continuous or not. So now, it's kind of hard to check continuity every single time, and so we have shortcuts for checking it. So we have the following theorem. So if f and g are continuous at a point A and c is a constant, then the following are continuous at A. So we have f plus g, f minus g, f times g, a constant times f, and f divided by g if g of A is not 0. So in other words, you can add, subtract, multiply, scale by a constant, continuous functions, and they stay continuous. And as long as you're not dividing by 0, you can also divide continuous functions and stay continuous at that point. And so this allows us to compute continuous functions very nicely. But we're actually going to have another theorem that is also going to be useful. And this comes from the theorem we just mentioned, along with some other arguments. And so we have the following theorem. The following are all continuous on their entire domain. So polynomials are continuous on their entire domain. Rational functions are continuous on their entire domain. Root functions are continuous on their entire domain. Exponential functions are continuous on their entire domain. Logarithmic functions are continuous on their entire domain. Trig functions are continuous on their entire domain. Now, with trig functions, you have to be careful. Some trig functions' domains are a little weird. So like tangent is not continuous at pi halves and minus pi halves, and then if you add any multiple of pi to one of those, you're also not continuous there. And so just be aware that they can have a lot of places where they're not continuous. It's just that they're continuous for all the points in their domain. And then inverse trig functions are also continuous on their domain. And so the short answer is almost every function you can think of other than a piecewise function will be continuous on its domain. Now, piecewise functions sometimes are, sometimes they aren't. But other than piecewise functions, most other things you can think of are probably continuous on their domain. Now, on their domain doesn't mean for every real number, as some of these functions' domains are not every real number. And so now we want to look at the following example of figuring out when a function is continuous using the facts that we just talked about. So we want to find where the function f of x equals ln of x plus tangent inverse of x divided by x squared minus 1 is continuous. And so now, as we mentioned before, when we take any functions, they're basically continuous on their domain. So ln of x is continuous on its domain. And its domain is 0 to infinity, not including 0. And tangent inverse of x is continuous on its domain, which its domain is negative infinity to infinity. X squared minus 1 is continuous on its domain, which is negative infinity to infinity. And so taking these pieces, we can put them together using our fact about adding functions to figure out where we're continuous. And so ln of x plus tangent inverse of x is continuous on, it's going to be everything from 0 to infinity, and it's also from negative infinity to infinity. So writing that in set notation, it's the intersection of the two places where they're continuous, which is equal to just 0 to infinity. And so natural log of x plus tangent inverse of x is continuous on 0 to infinity. And now we want to divide by x squared minus 1. We're kind of building up to our function f of x. And f of x, not f of x, x squared minus 1 is continuous for everything in its domain, which is negative infinity to infinity, but it's 0 sometimes. And so we have to be careful about dividing by 0. When x squared equals 0, that's when x equals plus or minus 1. So we can't be dividing by plus or minus 1. And so as long as we don't divide by plus or minus 1, we are fine. And so we'll just have to cut negative 1 or positive 1 out of our domain of 0 to 1. So our function f of x is continuous on 0 to 1 union 1 to infinity. Again, we have to drop out that point of 1 because we can't divide by 1, but we're continuous for everything else. And so here we were able to figure out where this rather complicated looking function of f of x was continuous just by using the fact we know functions are continuous on their domains, and we're basically just checking where these functions are defined. So next we want to talk about how do we deal with composition of functions. And so for composition of functions, we have the following fact. If f is continuous at b, and the limit as x approaches a of f of x, of g of x, equals b, then the limit as x approaches a of f of g of x is equal to f of b. In other words, the limit as x approaches a of f of g of x equals f of the limit as x approaches a of g of x. And so what this is saying, in a sense, is that we can pull continuous functions out of integrals, out of limits. And so here we have pulled our continuous function f out of our limit. Now, one thing to note here is this actually is allowing the direct substitution that we were talking about before. All that we're really saying here is the fact that when we're continuous at a point, we can plug stuff directly in. And since f is continuous at what the limit of g of x becomes, the limit as x approaches a of g of x, we said was b, f's continuous there, so whether we do the limit or just plug it directly in doesn't matter, since f was continuous there to begin with. This is just the idea of direct substitution that we've talked about before. And so if we wanted to do the following example, we want to find the limit as x approaches 1 of sine of ln of x squared. Well, we know sine of x is continuous for all real numbers, because that's the domain of sine of x. And so as long as ln of x squared exists and there's some value, sine will be continuous there. And so this is going to be the sine of the limit as x approaches 1 of ln of x squared. Now we know ln of x is continuous for all positive numbers, and x squared only outputs positive or non-negative numbers, to be more exact. And so as long as we don't get 0 in the limit for x squared, which we won't, we can pull ln out. So this becomes sine of ln of the limit as x goes to 1 of x squared. Now we know how to do the limit as x approaches 1 of x squared. It's a polynomial, it's just 1, so this becomes sine of ln of 1, which is sine of ln of 1 is 0, so we have sine of 0, which is 0. So we were able to compute this rather complicated looking limit by just pulling things out, which is a property that we gain from the fact that we are continuous. Now, this idea of pulling things out of the limit tells us how continuity and composition interact with each other. And so if g is continuous at a and f is continuous at g of a, then the composition f composed with g is continuous at a. And just as a reminder, f composed with g of x is f of g of x. Just as a reminder of how we write down compositions of functions. And so here we see that this idea of pulling things out is telling us that if g is continuous at a, and f is continuous at whatever g of a is, then the composition is continuous. And this allows us to check then when a function is going to be, a composition of functions is going to be continuous. So let's look at an example of actually using this fact. So we're going to have capital F of x is ln of 1 plus cosine of x. Okay, so it's a composition of functions, and so we have that the functions that it's a composition of is f of x, it's going to be ln of x, and then g of x is going to be 1 plus cosine of x. And so our capital F of x It's just f composed with g of x. So we need to consider when these are continuous. Now we know that f of x, little f of x, which is ln of x, is continuous on 0 to infinity. And so as long as we're plugging in a non-zero positive number, so a positive number, then we will be continuous there. And so we want to know, well, when is g of x continuous and when is it positive? And so we have g of x, which is 1 plus cosine of x. Well, this is a sum of 1, which is continuous everywhere, and cosine, which is continuous everywhere. So g of x is continuous on negative infinity to infinity. But now we want to know, well, when is 1 plus cosine of x outside of the interval from 0 to infinity? When does it take on 0 or negative values? Well, cosine of x is always greater than or equal to negative 1. And so 1 plus cosine of x is always greater than or equal to 0. So the only things we really need to be worried about are when 1 plus cosine of x is 0, as that's the only point that's going to be outside of the domain of our little f of x. So we're asking ourselves, when is cosine of x negative 1? Well, we know cosine of x is negative 1 at plus or minus pi, plus or minus 3 pi, plus or minus 5 pi. It's just all odd multiples of pi. All odd multiples of pi. And so we have to drop all of the odd multiples of pi out of our interval for when we are continuous for capital F. Because capital F will be discontinuous at those points, since f of g runs into problems at all of those points, since we'd be plugging in 0. And so we have that capital F of x is continuous. It's on negative infinity to infinity, other than the odd multiples of pi. And so we have to cut out those odd multiples of pi, because if we run into one of those, we have an issue. But other than that, anything we plug into little g of x will be totally fine. It's just going to give us out some value that we can then plug into f, and we would be continuous there. Now we can write this in interval notation as n pi, comma n plus 2 pi for any odd integer n. So that's another way of writing this down, of just saying from everywhere from n pi to n plus 2 pi, we are continuous where n is any odd integer.